for me at least. So you can take comfort in that, I guess, that it is really difficult for me to mark hard. But it is the only way that you'll actually listen to what I have to tell you. Okay, so a lot of marks were taken off for explain, right? And so the whole point of assignments and everything you do, in fact, that you give to me is to show me how much you know. That's school in general. Okay, so the whole goal is to show me everything that you know, and so you need to walk me through everything that you're doing, right? So if you're using the table C, right, tell me that you're using table C, right? And what you'll see in my notes, right, is that I do say using table C, we find this, blah, 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 right? So I'm constantly explaining what we're doing, okay? And that's what I want to see from you guys. I don't want you to worry. You guys always have outs in this course, I feel like. Let me just sort this out first. What do you mean by outs? Good question. As long as you do better on the final, I'll put the test weights on your final exam. You will have a chance to redeem yourself for assignment 3. I'm not just going to butcher you and then leave you there. Yes? Yes. Let's see here. I will be posting the solutions and we'll be doing something similar today. So, but yeah, if we still have questions or if we still have time rather, then yeah, how'd you get? So, okay. Oh yeah, the bonus for the test is always in the test.
Yeah, didn't you read the first question?
Wasn't this?
You're like, oh yeah, all right.
On test 1, no, I didn't. But in the future, should be explaining what you're doing. Of course, okay, so here's the deal. On the test, I understand that you're stressed and you're thinking about these problems and you're seeing them for the first time. I am a little bit more lenient on the test, right? You should still be trying to get everything out there, but on assignments where you have time to sit down and look back at my notes and look back at your notes, look at solutions to other problems, right? So I'm expecting more on an assignment than I ever would on a test, right? So, like I said, I'm just trying to set you straight. All these little nitpicky things are actually important. Okay. So, like I said, I will be posting the solutions. If we have time today, then absolutely we'll go through some of those, show you what happened. Okay. In general, despite the low marks, I'm not actually concerned about you guys. It's just good to get this. Bring the hammer down. Tough love. That's right. And like I said, it was really hard for me, so you should feel bad for me. Okay. So, but also, like I said, you'll have a chance to redeem yourselves. This won't be your, I haven't figured out what it is yet, but it won't be the be all end all. So a little bit of review, right? So last day we started talking about a mean observation, right? How do we find probabilities associated with a mean instead of just a single observation, right? So we talked about the sampling distribution. The sampling distribution of X bar, which we said was, okay, it's going to be X bar follows a normal distribution with a mean mu, the same as a single observation, and a standard deviation of sigma over root n, where the sigma over root n is the standard error, right? That's what we call it, because sigma, remember, is the standard deviation of the population, right? And so if we have sigma over root n as the standard deviation of our X bar, it gets a little bit tricky. So we just call it the standard error instead. And then we said, well, okay, we can still calculate Z scores, right, by using X bar minus mu. So again, seeing how far the mean is. So the sample mean is from the population mean. That's the same as we've been doing before. Okay. But now instead of over sigma, we've got over sigma over root n. So what happens is the standard error, or the standard deviation of X bar, depends on the sample size, right? So as n increases, so as your sample size increases, right, then your standard error is going to decrease, right? So the standard deviation, or the spread of your means, is going to decrease. Okay. So, and I'll just throw in here, and n is your sample size. I do expect you to know that, but it's been a weekend since then, so may as well throw in. Okay. So as n increases, the standard error, right, which is sigma over root n, decreases. Oops. The standard error is the spread of the means. The standard error is the spread of the means. So what we're saying is that as n increases, right, as we increase our sample size, the variability in our means that we're expecting to see gets smaller and smaller and smaller. So if you think about it, right, you have a set population, right, and I take a random sample, right, and I calculate the mean, and then I take another random sample and it's a little bit bigger, right, a little bit bigger, a little bit bigger, a little bit bigger, right. I'm getting closer and closer to the size of the population, right? And so that's why we expect our sample mean to become more and more stable as we increase the sample size, right? Because we've captured more of the population, right? So we expect a sample mean to become more stable as we increase the sample size. As we increase the sample size, oops. As we are I'll say using more of the population. our sample. I'll add that in our sample. So things kind of hinge on our sample size. Right? And then we did an example where we saw, what did we look at? We compared the assignment 3 question for a single observation, I want to say. And then we took a random sample of, I don't know how many salaries, just looking at the assignment 3 is about salaries, right? So then let's say we took 30 salaries, and now we wanted to look at the sampling distribution of the mean of these salaries, right? And then we saw that the standard error was much smaller than the original standard deviation. So, big review. So, we did an example last day. We'll continue with a little twist today, but looking at basically the same stuff. Okay. So any questions before we get going with the new stuff? So consider the formula for Z. Z is x bar minus mu over sigma over root n versus, this is the first time that we're seeing this formula for T, right? We have it on our formula sheet, but we haven't really looked that far. T is x bar minus mu over S over root n. Right. So looking here, ignoring the Z and the T, right? If I asked you what makes a T versus a Z, right? X bar minus mu, those are the same, right? The only thing that's different is that here we have sigma for our Z, right? And here we have S. Remember, S is our sample standard deviation, right? And then they're both over root n, right? So the only difference between a Z and a T is that instead of using the population standard deviation, we're using the sample standard deviation. Okay. So the only difference I'll even highlight this here and here. The only difference between a Z and a T is that Z uses sigma, right, the population standard deviation, and T uses S, which is the sample standard deviation. Nothing. It's just the T. What does Z stand for? Nothing. Just the Z.
Like those strips, like what does it correspond with? Because like the Z correspond with the Z score, is there like a T score?
There is a T score. In fact, we've been using the T table all along. Okay. So, riddle me this. If n, right? If n is our population, right? So if we increase our population or increase our sample size to include the entire population, right? Then our sample standard deviation becomes our population standard deviation, right? If our sample is the population, well, why are we doing anything? Then we know everything, right? And so T scores, right? As you increase your sample size, to include the entire population become z-scores. Okay? And so that's why, oh, does anyone not have the table? You'll want to have a table. I brought some extras today. Yeah, you bet. Have a loaner one. Anyone else need a loaner one? So, we've been ignoring all this middle section here, right? And just using the Z star line, right, so far, to find probabilities associated with a single observation or a mean observation, right? But now today we're going to start looking at all this middle ground here. Okay? It behaves the exact same way that we have been using it, right? Just we have to incorporate our degrees of freedom, which we'll get to. Okay? So, Oy. As n approaches, could say infinity, right? But approaches the population size, don't worry, no limits, no real limits. So as n approaches the population size, right, or n approaches infinity, right, population size is finite, but t-scores approach z-scores. Just as a fun fact. So what happens, because remember the difference between a z and a t is that we're using our sample standard deviation, which in real life, that's the only standard deviation that we'll have, right? And so in real life, we'll only be using t-scores. Okay? Z-scores are kind of the training wheels, right? So today we're taking those off and we're moving into t-scores, which are what we deal with in real life. Might have heard of t-tests, right? Oh, I just ran a t-test. No, maybe. It'll happen, trust me. Right, and so what we'll be doing eventually is we'll be doing t-tests. Okay? So in real life, we really only use t's, but we use z's because z's are this nice stable environment, right? The only thing that has variability, right, is our sample mean, right, or our single observation, right? So just because if we think about this room as our population, right, if I took a random sample of 5 people, right, calculated their mean height, put them back in, took out another 5 people, calculated their mean height, right? We know that the mean heights would be slightly different from group to group, but hanging around the same number, right? Yeah. And what happens here is that if we're using our sample standard deviation, right, then we're not only just calculating the sample average for each of these groups, we're also calculating the standard deviation, which is also going to be moving around with each of the groups, right? Hovering around some number, but there's going to be variability in S as well. Ugh. Right? So, okay. It's trying to not let it do that. Great. Okay. So to incorporate this variability in S into T, we use what we call our degrees of freedom. So degrees of freedom is this kind of weird thing, but all we need to know about degrees of freedom is that it's your sample size minus 1. Okay? Because the variability is going to depend on the sample size. Okay? So I'll write a lengthy note here. In real life, we will never know sigma, right? So we will have to use, oops, S, right? And so we have to calculate t-scores. T-scores follow a normal distribution. But the shape, so the area in the tails depends on your sample size. Okay. But the area in the tails depends on the sample size. And this is from that variability in S. Okay, you don't need to write that down or remember it or anything, right? But what we need to remember is that, okay, so a T distribution, I'll write down our degrees of freedom. We take this into account using our degrees of freedom. So degrees of freedom, df, is going to be n minus 1. So what happens is if we have a perfect z-score, so here we have z, it's nice. And then let me draw another one here. We have a T curve. But this curve is going to change. I had a nice graphic, but I don't know if I have it here. Forgot to bring it in. Probably not. Something like this, right? So here we've got our T, which has a little bit more room in the tails. What does that tell us? If the area under the curve, right, behaves the same way as what we've been seeing, right? So the area under the curve, there are probabilities still, right? But if we're leaving more room in the tails than we have before, right, we're just saying that, well, for small sample sizes, we don't actually know what's going on, right? We don't have a good grasp of what the population looks like, right? And so we're going to leave some room out here, right? Because the probability of being out here is a little bit higher than if we had the whole population, right? And so if we move down here, blah, blah. Oh, for some reason it's not in color, okay? But so up here in the dark line, we've got our normal distribution, right? That's our Z. And then here we have the closest one to it. This little guy here is 10 degrees of freedom. 10 degrees of freedom is a sample size of 11, right? I'd say that 10 degrees of freedom looks pretty close to a Z-score already, right? So we don't have to have huge samples. We just have to have samples that are kind of big enough, okay? Whereas degrees of freedom of 1 is this really faint line that you probably can't see, right? Kind of has big area in the tails, just to compensate by going lower in the middle, right? And then big area in the tails again. Okay. So, but degrees of freedom of 1 or 2, that's a sample size of 2 or 3, right? I don't think that any of us would set out and collect a sample size of 4 and call it a day, right? I think intuitively we understand that we need to have a little bit bigger of a sample for it to represent the population. Okay. So. So our degrees of freedom, right? As our sample size increases, our T distribution basically becomes a Z distribution. Right. So as, oops. As our degrees of freedom approach infinity, right? Or our sample size approaches the population size, the T distribution becomes the Z distribution. I might have already said that, but it's kind of an important concept. So looking at our, let's just call it the T table from now on, right? Table C, our T table, right? We have our degrees of freedom on the side, right? You only have one sample size, right? So you only have one row of degrees of freedom. So even though we have lots of rows to choose from, right? If I tell you that we took a sample size of 20, right? Then our degrees of freedom is going to be n-1. So we have 19 degrees of freedom, right? So then you can just ignore everything else on this page. And it looks kind of similar to the Z star line. Right? Trying to, doesn't matter, you can't see it anyways, it's so small. Okay? But so you just zoom in on your line of degrees of freedom. And then you go ahead and you calculate your T score, just like we've calculated your Z score, right? And then we can find a range for the areas in the tails, right? Approximate the area in the tail, find probabilities that way. So. What's kind of cool, I don't know if I should say this now or later. Yeah, I'll tell you now. What's kind of cool is that the T distribution, as long as we've collected a sample that's large enough, right, we know T follows a normal distribution, even if we're sampling from a distribution that's not necessarily normal, okay? Which means we can sample from anywhere that we want, right? Within reason. Okay? If we've collected a large enough sample from that group, the mean will follow a normal distribution. Okay. So, regardless of whether we are sampling from a normal distribution as long as our sample size is large enough, the mean will follow a normal distribution. That's pretty cool. Right? Especially because we only know how to find probabilities associated with a normal distribution, right? But it turns out that as long as we take a large enough sample, even if we're sampling from a distribution that's skewed, right? The average, as long as we're talking about the average will still follow a normal distribution, a T distribution. Okay? But if you compare even, so looking at your Z star line, the first number is 0.674, right? If you compare it, right, to even 30 degrees of freedom, right, sample size of 31, it's 0.683, it's 0.683, just moving up 0.683, 0.684. So they're essentially the same, right? Just kind of getting closer and closer together. So the same thing will happen as you move down this line, right? They'll get closer and closer to zero, right? Just kind of get condensed. Also looking at the far right one, 3.291, right? If you have, say, 20 degrees of freedom, 3.850, we're still in the threes, we're still in the high threes, right? And so nothing really changes except the slight change in the normal curve. But we'll still draw a normal distribution, we'll still treat it the same way, but if we're calculating a T, we also have to consider the degrees of freedom. Yeah.
Okay, so you just showed us that one thing where when the degrees of freedom went up,
Yeah.
like 10,
Yeah.
you would get closer and closer to that.
That's right.
Right? But on this one, if you were at degrees of freedom of 10, you'd get 0.700 instead of 0.674, and I think that's going the other way, it seems.
Yeah, so what happens
Like it's getting
if I pull this up here, I'll just go to this kind of simpler one.
It seems like 2 would be much more accurate than 0.816.
But, so here, let's say, so at this point, right, you've got, so at -2, a Z of -2, right, we know the area in the tail is, what, 0.025-ish. Here, the area in the tail is a little bit more, right? So we had to move out a little bit further to get the same area in the tail. I know. Because it's all about the areas in the tails.
Yeah, but I know, but you just, like that other drawing you just had there, where you got the list of
This one?
PDFs.
Yeah.
Okay, right there. Okay, I would think because the normal distribution is that boldest line.
Yeah.
DF equals 10, it's closest to the boldest line,
That's right.
right? So I would think it would be more of an accurate representation of what the distribution is, or
Yeah, so here, as we move and increase our degrees of freedom, right, we're also increasing our sample size. Because the degrees of freedom, right, is just your sample size minus 1. So exactly right. So as you're increasing your sample size, right, we're getting closer and closer to the Z distribution.
right.
On here, we're gonna see slightly, but
When you look at the degree of freedom,
for 10,
okay, just even for 10, it's a 700, 0.0700 or 0.700, but anyway, when you're at 1, you have DF equals 1.
yeah,
It's the furthest one down. It seems like it's most inaccurate.
that's true. It is the most inaccurate because what happens here is it's pushed down here because over here, it's this one with the most room in the tails. It's tricky, but as long as you remember that to use your degrees of freedom, then you already know how to use the t-table.
Okay, so how come the value increased? It looks like it would be more accurate if it was
Mhm.
0.0816, which would be a degree of freedom of 2. Degree of freedom 1 would be
Mhm.
0.00.
It's because it has to correspond to an area in the tail of 0.25, right? Looking at the far left column, right? These values have to correspond to an area in the tail of 0.25. See if I can get this going again. So the area in the tail, right? If we've got these low degrees of freedom, then we've got lots of area in the tail here, right? So to get an area of 0.25, right? Let's look on the positive side, right? Because here we've got an area of 0.25. We reach it faster than if we're down close to the, right? So we reach it faster at a Z or a T that's higher than the Z score. Right? But if you also look and go down the line, right, they're getting closer and closer to 0.674. Right?
Right.
So they're getting kind of compressed down onto the Z score. Right? Cool. It's a tricky concept to get. But as long as we know how to use it, we're okay. Okay. So we have to use our degrees of freedom. It's my take-home message. How about that? So when calculating T scores, we need to find degrees of freedom as n minus 1. If you're looking at your formula sheet though, we're in 5.1 now. Notice we skipped section 4.2 and 4.3. It's part of my get rid of the Z table spree. So we actually won't be using this 4.2, 4.3 section at all. So if you want to cross it out or whatever, ignore it. Same with the binomial 3.4 we didn't do. We won't be doing, don't worry. Okay. So you can cross those two out. So now we're in 5.1, okay, which has the title One Sample Mean, Sigma Unknown. Right? Sigma Unknown is just saying, instead of using the population standard deviation sigma, we have to use the sample standard deviation S. Right? And in the bottom of that box, I have the degrees of freedom as n minus 1. So I tell you how to find your degrees of freedom. So let's do a little example. I had a bigger example, but I want to start with a smaller example. Find the probability. I'll just do one. Find the probability of a mean greater than 30 if you have a sample size of 25 and a standard deviation of, I don't know, of 4, just making this up. Suppose mu is 21. Maybe 25. Should work out. So here, right, we can still draw our normal distribution centered on 25. Now we're saying that we have a mean of 30. And we want to know the probability of having a mean that's greater than this. We're told that the sample standard deviation is 4 and n is 25. So because we don't know sigma anymore, right? We know we have to use t-scores. Okay. So t is x bar minus mu over s over root n. X bar in our case is 30. How far is it from 25? If the standard deviation is 4 over the square root of 25. I shouldn't have used 25 and 25. Creativity is a little low today, I guess. Oh well. Should we change one? I'll change n to 23. Just so they're not the same when you're looking back at them. Okay, so we can calculate this. T's are going to tell us how many standard deviations or standard errors, and x bar is from mu, right? So the idea is the same. We've got 30 minus 25. 5 divided by the square root of 23. 4 divided by that. Oops. Thanks. I get 5 divided by 0.834057656. 5 divided by that guy. I made it too big anyways. 5.994789404. It's okay.
Would the sample size change to 23 or the mu change to 23?
The sample size we're changing to 23. Yeah. So we have a T of 5.99. Same rules apply as to Z, right? A Z of 5.994 or 5, I guess. Right. That's really huge. So we're way out into the tail. Same idea for a T distribution. Okay. So using T is 5.995. T needs at least 3 decimal places. Same as we've been using for Z's. And why is that? Because the table has 3 decimal places, right? So we have to have at least as many decimal places as the table does. Okay. So now, right, we have to find our degrees of freedom before we can, right? If we've calculated a T, we have to use the T section with our degrees of freedom. So our degrees of freedom is n minus 1, which is 23 minus 1, which is 22. So now you've decided that you have 22 degrees of freedom. Your sample size isn't going to change, and so your degrees of freedom aren't going to change either. Right? And so 22, that's our line. So what you're going to do is you're just going to block out everything else, ignore it all, just like we were doing with the Z star line, right? You were only looking at the Z star line. Now you can only look at the 22 degrees of freedom line. Okay. And now we try to place our calculated T on this line, right? We run out of numbers, but here's where we have to explain what we're doing. So my explanation goes like this. Using the T table, which we've been calling table C, whichever you want to call it is fine. As you'll see, table C is called the T distribution critical values. T table, table C, doesn't matter. So using the T table, with degrees of freedom equal to 22 now, right? If I'm using degrees of freedom, I have to say which ones I'm using. With 22 degrees of freedom, we find the absolute value of T equal to 5.995 is between 2 values. It is and it isn't, right? We only have one of the values on our table, right? If we go all the way out, right, we max out at 3.792. 5.995 is greater than 3.792, so we can put 3.792 down here. And technically, on the upper end, we have infinity, right? So if you wanted to, you could just leave it like this, right? Or I actually like to apply the same methodology to all of them, right? And so I'm going to say it's less than infinity. Right? That's true. 5.995 is less than infinity, right? It's way less than infinity. Okay. Using the same structure as before, right? So the one-sided p-value, or one-sided p, putting that in the center and wrapping it up in less than signs again. Okay. The one-sided p for 3.792 is 0.0005. And what we know is that our one-sided p, right, we're even further out into the tail. So our one-sided p must be even less than that. So our 0.0005 all we know, right, is that our one-sided p, it'll never be 0, right? But at infinity, the area in the tail, right, if we're out in infinity in the tail, the area beyond it is technically 0, right? So if you wanted a lower bound here, but it's important that you don't have a less than equal to, right? Because like we emphasized, the probability can never be 0, right? It can be approximately 0, which we're seeing here, right? The area in the tail is somewhere between 0 and 0.00005, right? Really, really small. So
How do we know that we're the 99.9 because we're looking to get to 100%? Is that why?
no, because we're going, so from 22 degrees freedom, we're taking our calculated t, and we're just trying to place it somewhere on this line. We find that we max out at 3.792, right, over here.
So our confidence level is not at 99.
We don't have our confidence level for this, for the probabilities.
Okay, because in the same time, what's the difference that we use that instead? Like 0.66.
Oh, because the whole goal is to figure out what the area in the tail is. The area in the tail is the one-sided p. So you want to go down. Right. Because here we started out and we said, well, what's this area in the tail? So this is our one-sided p.
Oh, like we're on this side of it. Because if we're doing it the other way, one on the negative side, then
Yeah.
we're using that one on
Well, because we look at the absolute value, right, if we had a smaller number than 5.995, yeah, we'd be closer in, which I was trying to get to, but on a whim, couldn't make up good numbers. Okay. So the question said, find the probability of a mean greater than 30 if you have a sample size of 25 and a standard deviation of 4. Suppose mu is 25. That's right. Thank you. Thank you, thank you. That would have been confusing if this wasn't already confusing. Okay, so our whole goal was to find this probability, right? That probability we'll just say is less than 0.0005. Right? So the probability of a mean greater than 30 is less than 0.0005. So here, right, I had to tell you, suppose mu equals 25. We go back, way back to the beginning of, I don't know, this course, I guess. I said the whole goal of everything that we do is going to be to try to predict what mu might be, right? And so from here on out, what we'll start doing is we won't have mu, but we'll try to figure out what mu might be, right? We have some hypothesis about what mu might be, right? And then we'll collect a sample and compare it to that hypothesized mean, right? And if they're close enough, then yeah, sure, the hypothesis is good, right? if our sample mean is way far away from our hypothesized mean, right, then the hypothesized mean is likely wrong. Right? And so from here on out, we're getting into hypothesis testing, right? And also confidence intervals. But confidence intervals are fun and quick and easy, so I'll leave those for a little bit. Okay? So what we're doing here, right? When I said, okay, suppose mu is 25, right? If we know what mu is, right, then why would we even bother collecting a sample and trying to figure out what the mean might be? That doesn't make sense, right? So our whole goal is to be able to collect a sample and then have some idea of what the mean might be, test it using the sample, right? And that's why it's important to have good samples, right? And then we can prove or disprove our hypothesis. So we usually won't know what mu is. Okay. We will have a hypothesis about what mu might be. So we collect a sample, right, to test our hypothesis. So we collect a sample to test our hypothesis. So let's do a little example. So the questions will be laid out a little bit differently, right? Because what's going to happen is I'm going to give you the sample information, right? The sample mean, the sample standard deviation, your sample size, right? And then I'm going to give you what you should use as your hypothesis. Right? Okay. So it'll look something like this. So you collect a random sample. You collect a random sample of 40 manatees. Cute. And you find their mean weight. Oops. To be 216 pounds. With a standard deviation of 31 pounds. So here's all the sample information that you've collected, right? Because so if you've collected this sample, right, and you find their mean to be 216 and their standard deviation to be 31, right, those have to be sample standard deviations, and those have to be sample means, right? If you found them, they have to be sample information. Must be sample information. So that's important to keep in mind, right? If it's something that we've done, right, it's always going to be sample information. Okay. So what do we have here? We're given that n is 40, right? We have a sample size of 40. We found the sample mean to be 216 and the sample standard deviation to be 31. Part A. What is the probability that the mean weight of all manatees is more than 200 pounds? What is the probability that the mean weight of all manatees is more than 200 pounds? All manatees, that's the population, right? So really what we're wondering, right, basically we have to find the probability that mu is greater than 200. Mu is the population mean, right? Here we're asking what's the probability that the mean weight of all manatees, right? So the population mean is more than 200 pounds. Okay. To test this, we have to assume that mu is 200, right? Because what we've got here is we've got our sample mean is 216. 216 is more than 200. What we're getting at is whether it's significantly more than 200, right? So we test this by assuming mu is 200. We know x bar equal to 216 is greater than 200. We want to know if it's significantly greater than 200. We want to know if it is significantly greater than 200. If it's significantly greater than 200, right, we've collected the sample, we found the sample mean, right? If we're confident in our sample, right, we've collected a good sample, right, then we're going to use that as evidence to say, no, the mean is actually not 200, it's going to be bigger than 200, right, based off of our sample mean. Okay. So in terms of the question here, what we've got is we're going to assume the mean is 200. We all have to blow our nose sometimes. We've all been there. But you're right, I should yell at him. Not really in my nature. So what we have, right, is we have this 200 that we want to test against, and we've got our sample mean of 216, right? So our sample mean is always going to be the one that we draw somewhere on the line, right? And then our hypothesized mean of 200 is the one that goes in the center still. Okay. So we want to know, right, what's the probability that the mean weight of all manatees is more than 200 pounds? Okay. So how we reflect that on here is, well, if I can find what the probability of this is, right? This is the probability of seeing, so collecting a sample with a mean of 216, assuming that the mean is 200, right? And if this area is big enough, right, if it's likely, right, then fine, the mean is probably 200. Right? There's nothing to say that it's not 200, right? Whereas if this area is really small, right, then we can say, well, it's pretty unlikely to collect a sample mean of 216, assuming that the mean is 200. So this area helps us determine how likely it is to have a sample mean x bar equal to 216 if mu is 200. Right. So what we say is, if this area is small, it is likely that mu is not equal to 200, but instead mu is just greater than 200. And that's all we need to be able to say. So to find this area, right, we're going to calculate a t-score and then use the t-table to find the one-sided p. So we've got t is x bar minus mu. Oops. Over s over root n. X bar is 216 minus mu, 200 we're using, over s, which was, I think we said 31, over the square root of 40. So we have 16 over 40 square root 31 divided by 4.901530373. 16 divided by that guy, I get 3.264286617. Do you guys get the same thing? Yes. So to 3 decimal places, I'm going to say t is 3.264. 4 to 3 decimal places. So now I'm going to use my T table, which means I have to find my degrees of freedom. I'm going to incorporate it into my explanation. So using the T table, with degrees of freedom equal to n minus 1, which is 40 minus 1. So degrees of freedom is 39. Great. Okay. Trying to look for 39 here. We don't have it, right? It goes from 30 to 40. And although it might be tempting to go to 40 because it's closer, right? We can't, because what does a degrees of freedom of 40 say? It means you have a sample size of 41, right? Which means you're pretending that you have a larger sample than you actually do. You can't do that, right? And so what we have to do is, for if our degrees of freedom aren't on here, we always have to round down, right? Because we can't say that we have a bigger sample size than we actually do. It's the logic there. Okay. So I'll just say using degrees of freedom equal to 30. And I'll just put a note about why later. Maybe I'll say always round down. I'm not going to put that there because that'll get confusing. You don't always round down. It's only if you can't find your degrees of freedom that you round down. If the degrees of freedom you're looking for aren't on the table, always round down to the nearest degrees of freedom. Oops. Okay. So I'm using 30 degrees of freedom. So I take a little sheet just to kind of, because I mean, it's really hard to not let your eyes bounce around on this sheet. It'll look the same. So now we find that the absolute value of t equal to 3.264 is between 3.030 and 3.385. $3.385. So now we have a range for our t, right? Just the same as we did for our z-scores, right? So our one-sided p is between two values. So now we can take our fingers and trace down from those values to our one-sided p, and reading them from right to left, right? We have between 0.001 and 0.0025. So what we know then is that the area in the tail is between 0.001 and 0.0025. So therefore, the probability of finding a sample mean of 216 assuming mu is 200, is between 0.001 and 0.0025, right? Really small probabilities, meaning it's unlikely. So it's likely that our sample came from a population where the mean is actually greater than 200. So it is likely our sample came from a population where the mean is greater than 200. Woof. Good work, guys. We'll keep doing examples next day. If there's something, so assignment 3, if you haven't got it back, or test 1, if you haven't got it back, then come grab it.